One of the subsets of problems you're going to start to see now in this semester are incline problems. So that's basically you have some sort of inclined plane. A lot of the times it's called a hill or various other things. It makes some angle with the horizontal. You'll have a mass on top of it. And you have to figure out something about the motion of that mass and what it's doing. Right? Not this week, but in the next unit, we'll add friction and other things to this. And so the question is, how do we approach a problem like this? So one of the first things that we'll mention is choosing your axes is really important. So for example, we could say, like we've been doing most of the semester, we'd make this the x-axis. We would make this the y-axis. But it turns out that's actually not a good idea for this type of problem, because then that means that you have your mass has to be moving in both the x and y axis. And so this is one of the advantages of being able to choose our reference frame, is that instead we can choose a reference frame where the x-axis is going down the ramp and the y-axis is perpendicular to it. So in the case of a sliding block, it's not going to be moving up and down on the y-axis now. It's only going to be moving in one dimension, x. And so it makes it a lot easier to calculate the actual motion of the object. So we draw a force diagram like you did in your book, or at least, like your book shows you how to do. So we can represent the mass as a dot. We know that there's going to be a force from the ramp on the block. We know that there's going to be the force of gravity on the block. So the question now becomes, again, if we call this the positive x direction and this is the positive y direction. Now we need to know what the gravitational force is in terms of these components, right? Because the gravitational force is pushing down this way on here. So the question is, what's the angle that it's making with our new x-axis? And a lot of the times, this is the most tricky part of the problem. And when I see students make mistakes on this, this is usually where your mistake is going to come in. And so here's the way that I think about problems like this. So what I do is I think about this in terms of right triangles. So I'll take this section of the ramp and I'll essentially make three right well, I guess two right triangles out of it. It's actually three, right? So we have our angle theta here, right? This is because this is that angle in the ramp. We have a 90-degree angle here, a 90-degree angle here, and a 90-degree angle there. Okay. Now, because of the basic properties of trigonometry, we know that this angle is going to be 90 minus theta, because all triangles have 180 degrees in them, and so if there's 90 degrees right in that corner, then the other two angles have to add up to 90. Well, so then that tells us that this angle must be theta. Okay? And so what that means then is that this angle is theta, because right here is 90 minus theta. So going back over to our force diagram, we know that this angle is theta. So that means when we're looking at the x components, if we sum all the forces in the x direction, we see that we only have one force right now, right? So it's the force of gravity on the block. It's the sine theta component. Now again, most of the other problems that you're working, right, the x component is cosine theta, but in this particular instance, because of this, the configuration and the angles that we've been given, it's sine theta. Now, if I had called theta this angle, then this would be cosine theta. So if you don't understand that, pause the video, think about it for a minute, maybe go back and watch it again, and make sure you can convince yourself that that's true. So you can't just assume there's one formula that always works. But in this particular case, for this configuration, the sum of components in the x direction, the sum of forces in the x direction is going to be the force of gravity times sine theta. And then if we look at the y components, right, well, we've got two forces. We have the force of the ramp on the block, and we have minus the force of gravity on the block cosine theta, right? That's this component right here. Okay, and we know that that's zero because the block isn't accelerating at all in the y direction. Now for this particular problem, if all we're trying to do is find the motion of the block, then in that case we could just ignore the y component, right? We don't care about that at all because it's not moving in y. But you'll see problems later in the semester where it's important. For example, sometimes we're going to have to find the force of the ramp on the block, also commonly referred to as the normal force. And so, for example, that may be important if we have a second mass on top of that mass, right? Because now we have an additional force component, right? This is going to be the force of mass 2 on the block. So now we have an additional minus force of mass 2 on the block, right? And so we can add as many things into this picture as we want now. The key was making sure that we set up our diagram using the correct coordinate axis and made sure that we kept track of all of our angles in this axis, right? Because now, even if we had other forces going, either forces happening, right? We could do the same trick here, where then we know that this, because this is 90 minus theta, that this angle is going to be theta. And you can just keep dividing it up that way. So that way we can always keep track of what the angle is and making sure we're using the right angle. Because it's using the right angle and keeping track of all the components that's going to be the trick to this problem.